I was away yesterday, so I was not able to attend the previous lectures, but I look forward to the lectures for the rest of the week. I want to talk to you about a relatively new problem in hyperbolic PD with most applications in general relativity, which is the characteristic gluing problem in general relativity. So the ultimate goal is to discuss this problem for the Einstein equations in a very specific setting, the characteristic setting. But in order to get there, I will first start with something way more basic. So today will be a very, very basic introduction to this problem, where we will discuss basically the simplest PD one can write down, which is the wave equation. Okay, so we'll consider this problem for the simplest, in the simplest setting. All right, first of all, what is the problem? The problem in general of the gluing problem in general in geometric analysis is a problem where we are given two geometric domains. So we're given D1, we're given D2, we assume that they are disjoint. We're not trying to merge, we're not trying to match, we're trying to glue. So glue has a very specific meaning here. We're giving two different domains. We assume that in each of these two domains, we solve some field equation, whatever that is. Like there is something, there is a law being satisfied in each of these domains. And we want to find a bigger domain containing both of them, such that in the big domain, as I said, the big one contains both of them. That's the first thing we need. The second thing we need is that in the big one, you have this equation, this field equation being satisfied. That law is also satisfied in the big one. And third of all is when you restrict that law in D1, you get whatever you had in D1. And whenever you restrict the law of in D2, you get what you had originally in D2. So the existence of D is what we call the gluing of D1 and D2. That's the gluing problem. Okay. So the ultimate goal is the equations 1, which is the Einstein equations. All right. Here I have written them in vacuum. So basically, this is we can assume that D1 and D2 are four-dimensional Lorentzian manifolds in which you have a Lorentzian metric which satisfies these equations. Now, since the right-hand side here is 0, these are the vacuum equations, which are equivalent to having the Lorentzian Ricci curvature being the trivial tensor, like because the scalar curvature is 0, too. Okay, and all right, this is the Einstein equation. So that's one equation we could try to glue. So that's like gluing space-times, if you do this at the level of these questions. Another equation that you could try to glue is something you obtain. It's a subset of this set, which is what we call the Riemannian constraint equations. So what are these equations here? They're simply the following. So the Einstein equations are satisfied in a Lorentzian manifold. So let's say this is time-like direction, this is space-like direction. If you consider a space-like section, a space-like hypersurface of your manifold, then the induced metric here will be space-like, right? It will be Riemannian. And now the Einstein equations actually impose conditions on that Riemannian metric. And these are what we call the constraint equations. So the equations are not just at the level of G, but they're also at the level of the inbending of sigma in in M. So you also need the second fundamental form of sigma. So for this triplet here, we have these equations. Okay, this is the Riemannian scalar curvature now, and this is the second fundamental form. And again, here, divergence of the second fundamental form, the gradient of the trace of the second fundamental form. Everything here is purely Riemannian, and it's defined for the Riemannian slice. So this is, again, it's a subset of these equations, okay? So this is a type of law that, you know, any Riemannian slice in space-time has to satisfy. So now you could say that instead of trying to glue space-time, so instead of D1 and D2 be four-dimensional Riemann manifolds where you have the Einstein equations satisfied, you can assume that each of these D1 and D2 are basically portions of space-like slices. And the equations now you are trying to glue are not the Einstein equations, but the Riemannian constraints, okay, these ones. So this problem is a very important problem in general relativity and geometric analysis more generally. This is what's known as the Riemannian gluing problem in general relativity. I won't focus a lot on the Riemannian problem, even though at the end we will see that the characteristic gluing problem can actually provide and recover and even improve a few results from the Riemannian gluing problem. But what I would like, so today, as I said, I don't want to really talk about the Einstein equations, but just since it is generality, let me just give you one result that's known for the second problem, where we are trying to glue not space-times, but we're trying to glue space-like slices. So this sigma 1, space-like slice, satisfying the Riemannian constraints, sigma 2, and you want to see if there is a bigger slice, as I said, gluing those two. Oops. All right, so the result says that this is one of the most important results in this direction. If you start with an asymptotically flat solution to the constraint equations, which basically means that this guy asymptotically at infinity, and again, you can define it in terms of some coordinate that grows. This guy that you start with, asymptotically at infinity, basically converges to the Euclidean geometry. And the second fundamental form goes to 0. So that's what it means to have an asymptotically flat slice. Then that slice, you can actually, so if this is asymptotically flat, you can cut it at some point and then glue with something further out, with something that you know very well, which is the Riemannian slice of a very specific space-time. And that space-time is a Kerr space-time. So the Kerr space-time is it's an explicit solution as space-time to the Einstein equations. It has it's parameterized by two parameters, the angular momentum and the mass. And what happens is that given an arbitrary asymptotically flat slice, you can glue it asymptotically far, far away from any bounded region to a specific Kerr, okay? To some Kerr, not every Kerr. So you have to choose these parameters very carefully. And that's a nice thing about Kerr, that it allows you to do some you can use the parameters to do some fine tuning. All right, so if you have the Riemannian constraint equations decaying to 0, then far away where they decay, you can basically glue them, truncate them, and then glue them to something very, very specific and explicit. Okay, and as I say here, space-like hypersurfaces are extremely important from the point of view of the Einstein equations and its dynamics. Because after all, when we solve the Einstein equations, right, we want to solve them knowing at some point, the space-time and then solving the future. So that's the context of the Cauchy problem. In the Cauchy problem, you start with a Riemannian slice, the metric there, the second fundamental form, and then you let the Einstein equations evolve that slice into space-time. So space-like hypersurfaces are very important, and gluing them are also very important. So this problem here is basically the problem of gluing initial data for the Einstein equations. Okay. And what this theorem tells you is that you can glue any asymptotically flat initial data far away to the data or to the Riemannian data of a Kerr family, some Kerr family. All right, and now we will start the main topic, which is the characteristic gluing problem, okay? So very informally, this is space, this is time, these are the characteristic directions, okay? So instead of gluing, this kind of gluing here involves gluing in both space and time. This gluing here involves only gluing in space. And what I want to understand is gluing not in time, not in space, but in the characteristic direction. That's basically what the characteristic gluing is. But let's see a few pictures. So first of all, the characteristic surfaces instead of Riemannian surfaces are what? They are surfaces that have the property that the normal is tangential to your surface, okay? In other words, the normal vector is a null vector. And a null vector, as you all know, is normal to itself. Okay, that generates a lot of strange things. Having the normal being tangential to your surface. Since the normal is tangential to your surface, that means you can take the flow generated by this tangential vector field. In other words, you can take the integral curves of your normal vector field. And these integral curves, which will of course be tangential to your surface. So here we look at C0 only, forget about C0 bar for a second. These are the integral curves of the normal vector. And the main property of these curves is that they are null geodesics. They are null curves because, of course, the normal is null, so they have to be null curves. Like think of them about all being 45 degrees. But they are geodesics, okay? These are geodesics of your spacetime. All right, and exactly the same happens to the other hypersurface here, C0 bar. These white things are the null geodesics generated by the normal vector field. These null geodesics are called the null generators of your null hypersurface. Now, C0, if you assume that we are talking about four-dimensional spacetimes, C0 is a two-dimensional sphere. Okay, this is a two-dimensional sphere. And now, starting from any such two-dimensional sphere, we can produce precisely two null hypersurfaces containing sigma 0, and moreover, being orthogonal to sigma 0 at sigma 0. Okay, so if you consider any vector if you consider the vector tangential here to the null vector, if you consider this null vector here, this null vector is orthogonal to any vector tangential to sigma 0. So the family of these geodesics is what we call the null, because they're null, normal, because I just said the white is orthogonal to the black. So it's null, normal, geodesic congruence. Okay, generating or emanating from the points of S0. And that one is basically the outgoing, and the other one is the incoming. And for any such section, there are precisely two such null congruences, okay, which are normal to S0. This is extremely important to understand anything, basically, that has to do with characteristic surfaces in general relativity. So C0 we call the outgoing null hypersurface starting from S0, and C0 bar is the incoming or ingoing null hypersurface starting from S0. And if you're not very familiar with this, but you want to understand, what I'm saying is that if you consider, for example, this space-time, two-dimensional space, one dimension in time. So this is space, this is time, and you consider a space-like vector, okay? Then the normal to this space-like vector is what? It's a time-like plane. And what's the dimension of this time-like plane? It's 1 + 1. Okay, it's a two-dimensional Minkowski plane. And in a two-dimensional Minkowski plane, you have precisely two null directions, precisely two. One and another one. Okay, and so what is the property of these two null directions? They're null and they are normal to this guy. Okay, exactly. This is exactly what you do, but instead of doing it in 3 dimensions, in 3 total dimensions, you do it in 4. But you still get 2 null directions orthogonal to your section. All right. Now, as if you consider just the outgoing section, outgoing null hypersurface for a second, and what you can do is you can start with a 0, and then you can flow S0 along the outgoing hypersurface. Okay. And that flow can give you other sections of S0, like this one here. And similarly, you can flow S0 in the incoming direction and get other sections in the incoming hypersurface. So a null hypersurface is generated by these null generators, okay? Or here the outgoing one is here. But at the same time, it's also foliated by not one-dimensional objects, but by two-dimensional objects, these spheres here. These are null geodesics. These are Riemannian manifolds, Riemannian spheres. Both of these, the null generators and these sections, these Riemannian spheres, will be of extreme importance when we try to study the geometry of null hypersurface. The null hypersurfaces in the setting we have already introduced allow us to define what we call now the double null foliation of spacetime. Geometry is all about understanding foliations of something with something. These are foliations of null hypersurfaces with curves or with spheres. Now, this picture depicts foliations of your spacetime with null hypersurfaces. And because it's a 2-parameter such family, you call it double null foliation. So how do you form the double null foliation? Okay. It's actually very easy. What you do is you consider 1-parameter family of such outgoing null hypersurfaces. This family is given by the level sets of some function, the level, okay? And you want the level, each level sets of that function to be a null hypersurface. If this is true, then your function is called an optical function, if its level sets of null hypersurfaces. And then you consider a second optical function that has the property that its level sets are null hypersurfaces. Okay, and now you can consider the intersections of these null hypersurfaces. You can start with an intersection here as 0, and you can have this being your starting section of your double null foliation. All right, start with the 0, then one level set is outgoing, another level set of the other optical function is incoming. And along this outgoing one, you can have these level sets intersecting that one, and that gives you the family of sections here. And along the incoming one, you can have these null hypersurfaces intersecting that one, and that will give you a family of sections here. And what I just said, you can do not only for the initial outgoing and the initial incoming null hypersurface, but for any outgoing null hypersurface and for any incoming null hypersurface. So any outgoing null hypersurface will intersect some incoming null hypersurface, and the intersection will be some 2 sphere. Okay? Then what have we achieved? We have achieved that we have foliated the space-time with a family of outgoing null hypersurfaces, with a family of incoming null hypersurfaces, or with a 2-parameter family of spheres, which are the intersections of these guys. Let's see. I don't know if I have a picture. Maybe next time I'll have a better picture. But yeah. So as you see here, the intersection of any two of those two null hypersurfaces give you a sphere. Okay, and the family of all these spheres foliates your space-time. So now understanding the space-time geometry basically reduces to understanding the geometry, intrinsic and extrinsic, of those spheres. Okay, that's why in understanding space-times we have a lot of elliptic structures, because many of the equations are elliptic on these spheres. All right, so as I said today, I don't want to, and time passes very quickly, I don't want to talk too much about the Einstein equations. So maybe I continue this discussion for the double null foliation, double null coordinates, and how exactly we define them next time, because this is when we will need them to understand better, the characteristic gluing problem for the Einstein equations. For now, what I will say is that, so very quickly, is that this construction here, the two optical functions, can actually be upgraded to a coordinate system of your space-time. Two of your coordinates are the optical functions. If you know their value, then you're on a sphere. Then you need two more spherical coordinates to know at which point of that sphere you're on. It's very interesting to know how to define these angular coordinates, because basically this is what gives you three-dimensional direction in your space-time. Okay, that's very interesting. And this is what I'm trying to do here with the picture, but next time we'll discuss this. So since we have a coordinate system for our space-time, we have coordinate vector fields. And using these coordinate vector fields, we can express the metric. And the metric in terms of these coordinates takes this form. Okay, it's much simpler than having an arbitrary coordinate system and writing your four-dimensional Lorentzian metric in terms of the arbitrary one. All right. Let me very quickly say a few things. This omega here basically tells you how you move from one section here to another section. If these sections are equally distributed along your hypersurface, then omega is 1. If you have sections going extremely close to each other, then omega will tend to 0. If they diverge, then omega will grow. Okay, so omega tells you how your sections are separated. Okay. And this phi here basically gives you the size of the spheres. So think of this as being a unit sphere on each of the sections. On each of the sections here, you have a round metric, unit round metric. And phi basically is the factor that compares the induced metric with that round sphere. Okay, again, next time we'll be more specific. But this conformal factor gives you somehow the radius, and omega, as I said, gives you how these null laps, how the spheres are separated. Now things are getting more complicated because, okay, it's nice to have a coordinate system, but it's even nicer to have a frame. Frame does not have to be a coordinate vector field, right? Not a family of coordinate vector fields, just has to be a basis of vectors. And we can use the coordinate vector fields to construct what we call a null frame. So vector fields which are null, two of them which are null, and two of them which are purely angular. So we have a frame of 4 vectors at each point spanning your space, 2 of which, as I said, are null, and 2 of which are angular. And using this frame, you can define all your geometry. So what does geometry mean? It means 2 things for your Lorentzian metric. It means first-order derivatives, and it means second-order derivatives. These are the Christoffel symbols. These are the curvature components. Even for the wave equation, we will need just to know some of them. So this is the second fundamental form of sections, chi and chi bar. This is what we call the torsion. That's very specific geometric meaning. And these are all curvature components, but we don't need them today. So the second fundamental form in the outgoing direction is this one. The second fundamental form in the incoming direction is this one. You see, we differentiate the outgoing vector in the angular direction, and we project it in the angular direction. So basically, this is telling you how the sections, the sections change when you move them along the respective null hypersurfaces. And this second fundamental forms can be decomposed into the traceless part, which basically tells you how the conformal part of the metric changes, and the trace part, which basically tells you how the radius is changing, the conformal factor. Okay, this is the shear, and this is the change of the radius somehow of your spheres as you move the sphere along the null hypersurface. So a very important example, if you have a null hypersurface which in the direction of L is expanding, then the radius, although we don't talk about radius, we talk in terms of conformal factors, but the radius is increasing, right? And as I said, this guy here is giving you how the radius changes. It's the rate of change of the radius. So if your hypersurface is expanding, this guy must be positive. If your hypersurface is collapsing in the direction of your null vector, then the change of the radius has to be negative. So this guy is negative if it's collapsing. And what's very interesting is that there are surfaces, right? There are spheres. There are spheres that have the property that both, as I said, given a sphere, there are exactly two null hypersurfaces that you can take from starting from that sphere. Two null normal congruences forming two hypersurfaces. And there are spacetimes where both of these null hypersurfaces have the property that this expression is negative. So in other words, as you move towards the future, both of your null hypersurfaces, the outgoing one and the incoming one, are collapsing. Okay, such sections do not exist in Minkowski, but they exist in spacetimes under various conditions. Okay, and these sections are called trapped. Now, in Minkowski spacetime, there are sections that have this property at some points, not at all points. Who can give me an example of a section in Minkowski where you can have both hypersurfaces starting from that section being collapsing? It's actually very easy. Do the start inversely. Take a standard cone that's collapsing towards the future, and take one more null cone, right? That's also collapsing towards the future. And what you do is you intersect these cones. So the intersection here, although it looks like it's time-like, it's actually space-like, because it's a section of null hypersurfaces. And as we said, they have to be space-like. So if you consider the intersection, you see the intersection, this guy here starts two hypersurfaces. That's the first one. That's the second one. There cannot be anything else, because we could define that guy as intersection of null hypersurfaces. And both of these null hypersurfaces are collapsing. The thing is that this guy here is not compact, okay? So it is collapsing at all points. Like it is trapped at all points, basically, but it's not compact. It's not a two-dimensional sphere. So what you can do is, if you want something compact, then you keep your surface up to this point, and then you do something like that. Okay, to connect them. Now you made it compact, but at these points here, of course, the collapse property you have killed. Anyway, the only reason I'm saying this is just so that we get a little bit familiar with this notation here, and it's their geometric meaning. as you already saw, it's very important to understand how things evolve, how they change, what's their derivative along the outgoing and the incoming direction. And so we have these two operators that basically correspond to this. What is your derivative in the outgoing and your derivative in the incoming direction? And finally, we can introduce the characteristic gluing problem, which is the following. Consider a section and portions of the outgoing null hyper surface and the incoming one, starting from the first section. And then consider another section and another portion of its outgoing and incoming null hyper surface. You want to know whether somehow this domain here can be glued to this domain under certain circumstances, of course, always. What are the equations you're gluing? What are the information you have here and here and everything? But that's the problem, okay? You have two bifurcate null hypersurfaces, two such domains, and you're going to see if you can glue them. So you start with this, and you want to know whether there is a null hypersurface extending this one. And then if you continue, you get into this one, such that along the red one, you can extend whatever field you had defined here. And as you extend it, you get the original field of that domain. That's the characteristic gluing, okay? So in 2 dimensions, it is what I told you before somewhere. Now, something very interesting happens is that instead of considering the surface, these two spheres, nearby null hypersurfaces, what you can do to simplify the problem is just stick with the spheres S1 and S2, and on S1 and S2, simply take whatever information these transversal hypersurfaces give you. So instead of having your field here and here, and information far from S1, and information far from S1 again, and far from S2, and far from S2, you just consider whatever information you have exactly at S1 and S2, or at directions transversal to S1 and S2, but at S1 and S2. So instead of considering this, you consider something less. This is not a reduction, it's a simplification, like it's less information that you consider. You consider something here on S1 and S2. And then you wonder whether there is one null hypersurface which admits S1 and S2 as two sections. And along this null hypersurface, you solve some equations. And when you reduce your field on S1, you get what you started with at S1. And when you reduce at S2, you get what you started with S2. Okay, this is actually the characteristic gluing problem we consider for all cases, for the Einstein equations, for the wave equations, for everything. Okay, this reduced problem. Let me start again with the discussion of the characteristic gluing problem, but instead of using these 3D pictures, which although are more intuitive, they might be more confusing. Let me just repeat what I just said with 2D pictures. So what is S0? S0 here is a point. Because instead of considering all angular directions, right, I collapse all angular directions and I consider just one angular direction, which means basically I only consider one point on each sphere. So a whole sphere now is basically represented by a point. So this is a whole sphere. The incoming null hypersurface is this one, the outgoing is this one. So that's the first sphere you start with, that's the second sphere you start with. This is the incoming outgoing null hypersurfaces, incoming outgoing null hypersurfaces. If you consider data here and here in the blue pieces, and on the green pieces, then by the characteristic theorem, you have solution to your field equations, whatever equations you consider, in this region and in this region. Okay, and now one gluing problem would be, the most honest version of the gluing problem would be, okay, if you have data here and here, you have a solution here. If you have data here and here, you have a solution here. Then try to extend this green thing in a characteristic way so that you hit S1, so that you make this whole guy into one null hypersurface. And moreover, once you do this, input data here, so that when you consider this data, you get a solution here. And that solution you get here perfectly matches the other solution here. Okay, that's the, but that's a very difficult version of the gluing problem, because if you remember, when I started talking about the gluing problem, I talked about two problems: gluing of space-times and gluing of data. Right? That problem here corresponds to gluing space-times. So it's very difficult, because this is you're gluing this space-time to this space-time. Instead of doing that, we want to consider a version of this form, where we're gluing basically data. But the data are not in the null direction, are not in the space-like direction. I want them to be in the null direction. That's why this is not a problem to consider, but this is a problem to consider. Okay, so I forget about this whole portion here, this whole incoming null hypersurface, forget about all this. And I only stick on this one null hypersurface, and everything in the transversal direction, I only have it at the level of a derivative here. Just one transversal, or as many transversal derivatives as I want, but at this point, I don't go here, 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 here. Once I go here, I form a space-time, and then I have to glue space-times. Once I stick here on this line only, and I just have transversal derivatives, but only on this line, then you see this is only information on the line, so that's basically data. So even better, that's what I say here. Yeah, start with whatever data you want here, whatever data you want here. Try to form a null hypersurface connecting them, so that when you solve the equation along this one null hypersurface, everything here, everything matches basically. There are no discontinuities along this one null hypersurface. And even better, forget about, so as we said, we forgot about this incoming piece. You can also forget about this whole thing. Instead of having data on a whole portion of an outgoing null hypersurface here and here, just forget about this and stick with S0 and S1. Keep at S0 whatever you have in this direction, in this direction, and keep at S1 whatever you have in this direction. Okay? And that gives you this. You have data at S0 and S1, and you want to find a null hypersurface, solving your equations, whatever they are, and matching at the boundary of this null hypersurface your data at S0 and S1 you start with. All right, so this is the characteristic gluing problem. Okay, and the way I formulate it is for any kind of equation, as long as it's hyperbolic. So you have a version of a characteristic initial value problem. Now, let's see the simplest case for this problem, which is the wave equation. Before I give you the results for the wave equation, let me say something. What would be one difficulty in gluing given sphere data at S0 and given sphere data at S1? One difficulty will be if for any null hypersurface connecting S0 and S1, you have that along this null hypersurface, you have the conservation law. So any conservation law is an obstruction to gluing. Because if your data here are very general and your data are here very general, and you have a conservation law along this null hypersurface, and say this conservation law tells you that the expression here is conserved along this alpha surface, and the expression given by the data at S1 is 1, but that expression given at the by the given data at S1 is 2, then you can immediately see that this conservation law does not allow you to glue S0 to S1. Because if you have such an alpha surface, the expression here will have to be equal to this by the conservation law. But on the other hand, if you start with general data for which the conserved quantity here is 1 and the conserved quantity here is 2, that tells you that those two data cannot be glued. So conservation laws in general, we should know, are obstructions to gluing. Okay, whatever conservation laws, again, very general discussion. Now it's the moment where we finally specialize the discussion, and because everything I said so far is at a very high level. All right. So what do we do now? As the simplest case, we fix the geometry. The metric we assume is given. For the Einstein equations, the unknown is the metric. Now, I assume that the metric is known, okay? G is known. I give you a general, smooth, regular Lorentzian manifold of dimension 4. So that means I know the null hypersurfaces, since I know the metric. I'm not solving for the null hypersurfaces, but what I'm solving is for a field on the Lorentzian manifold. And in this case, just a scalar field. So what I want to do is the following. I consider an arbitrary, I consider an null hypersurface. I consider two sections on it. I prescribe data for psi on S1 and data for psi on S2. Let's say I want psi to be whatever I want here. I want psi to be whatever I want here. And derivatives, space-time derivatives at S1, I can also prescribe them here. And space-time derivatives for psi, I can also prescribe them here. And I ask, is there a way to extend psi on the null hypersurface connecting S1 and S2 here so that the wave equation makes sense for psi? The wave equation imposes constraints on what psi can do on a null hypersurface. So when you require the wave equation, and moreover, you require your data to be prescribed here and here, that's an overdetermined problem. And you want to know whether this overdetermined problem has a solution. That's the gluing problem in the characteristic direction. And here is the first result. Characteristic gluing problem for the wave equation on a given general Lorentzian manifold is possible only in general if there are no conservation laws on your given null hypersurface. In other words, the only obstruction to gluing on null hypersurfaces, scalar fields, are conservation laws. If you have no conservation laws, then you can glue any data to any data. All right? The only thing that can stop you is conservation laws. Now, one could again be wondering, what are these conservation laws you're talking about? Well, I promise you, you have seen many such conservation laws before. Here's the theorem. Let me skip it for a second, and let me give you examples of conservation laws that I'm talking about. Let's start with the simplest space-time, which is the Minkowski space-time. Okay? If you write the wave equation, and moreover, let me simplify this a bit more. And moreover, you consider null coordinates. This is the V, this is the U. Then the wave equation in Minkowski. And moreover, in spherical symmetry, zeroth angular frequency is dV, du of r psi, r is the radius, or standard radius, equals to 0. That's the wave equation. So this is the outgoing derivative, null derivative, this is incoming null derivative. What is the wave equation telling you? It's telling you that if you move in the outgoing direction, this transversal derivative, this du derivative of r psi is conserved. the wave equation itself in Minkowski gives you conservation law immediately. But in order to see this conservation law, you have to express the wave equation in null coordinates. These are the double null coordinates I tried to introduce before, but for the simplest case of the Minkowski spacetime. So this derivative is 0 means that this derivative is conserved. This derivative is this derivative here, being conserved as you move in this direction. All these derivatives are constant, have the same value. All right, so if you start with a sphere, you move in the outgoing direction and you end up at another sphere. And you have here a transversal derivative of your scalar field, and here a transversal derivative of your scalar field. Those two derivatives have to be equal. So if you prescribe data where the transversal derivatives are not equal, and you try to find psi that glues those two non-equal transversal derivatives, and moreover psi to solve the wave equation, that problem is not possible. Okay. Now I consider the spherical symmetry. Of course, for the general scalar field, you can just integrate over the spheres and keep only the spherical mean. So this is a conservation law along sections or along null hypersurfaces, the standard null hypersurfaces of Minkowski. What are they? They are integrals over the sections of derivatives of your scalar field. Such conservation laws are very important. One, if you want to do something this evening, for example, is to use these conservation laws to prove Strong-Huygens principle for the wave equation in 4 dimensions. All right, let me give you another application, another form of the conservation laws. We have Minkowski, which is perfectly flat, but you can also have spacetimes which are asymptotically flat, not everywhere flat, but asymptotically flat. I already talked about asymptotic flatness of initial data. Okay, now you can consider that you have asymptotically flat spacetimes. Basically, as you go to infinity, the spacetime converges to Minkowski. Then you asymptotically get a conservation law at infinity. Right? In Minkowski, you have a conservation law everywhere for all null hypersurfaces. If your spacetime is Minkowski at infinity, then you get a conservation law at infinity. And this is a conservation law. Okay? As your scalar field, as you measure your scalar field at infinity due to dispersion, your scalar field goes to 0. And that's why you have to rescale it to make your derivative non-zero. And that non-zero derivative at infinity is conserved as you move from one section to another. This conserved quantity is known as the Newman-Penrose constant at infinity. And again, this is true not just for Minkowski, for any asymptotically flat spacetime. What are examples of asymptotically flat spacetimes? Mixed parts spacetime, Kerr spacetime, Riese-Nordstrom spacetime. All of these spacetimes have a Newman-Penrose constant for the wave equation at infinity. Now, I can be a little bit more precise. This is time like infinity. This is space like infinity. It doesn't matter what happens to the space-time here. What matters is that these two guys are connected by what we call null infinity, right? And here, your geometry basically is very close to the geometry of Minkowski. This null infinity is an incoming null hypersurface. This is where outgoing null geodesics terminate. Okay, it's like the end point of outgoing null geodesics, which go very, very far. The area radius goes to infinity. And the collection of these endpoints gives you an incoming null hypersurface, which is the future null infinity. We can think of future null infinity as simply being an incoming null hypersurface in Minkowski. And along every incoming or outgoing null hypersurface Minkowski, you have a conservation law. So the conservation law rescaled that you obtain along this null hypersurface is precisely the Newman-Penrose constants. Okay, it's a conservation law along null infinity. Let me give you one more example. So I'm going to discuss more technical details tomorrow, but for now, we talked about Minkowski, we talked about null infinity. Let's talk about black holes. Well, this is a heuristic picture of what a black hole spacetime looks like. This is the event horizon. Here inside is the black hole. This is the domain of outer communications. This is null infinity that I just talked about. If you are in the domain of outer communications, you can go to null infinity, or you can cross the event horizon and get in the black hole. But once you are in the black hole, you can never exit it. You can never go back to null infinity, because you have to move always in your future. All right, so this spacetime has null infinity. So for this spacetime, we have a Newman-Penrose constant here. If your black hole spacetime is what we call an extremal Reisen-Nordstrom spacetime, this is a spacetime. Reisen-Nordstrom is a family of spacetimes with two parameters, the mass and the charge. Okay, it's a solution to the Einstein-Maxwell system of equations. So we have mass and charge. Now, if the mass and the charge have a satisfied relation, then we call this spacetime extremal. In the extremal case, we have a conservation law for the wave equation along not just null infinity, but also along the event horizon. Okay, the event horizon is an outgoing null hypersurface. You can consider sections to the event horizon. Along each such section, you can integrate an expression of your scalar field that involves the scalar field and its derivative. In this case, it's the transversal derivative. And the result you get is the same, regardless of the section you chose, for any solution to the wave equation. So that's a conservation law for the wave equation along the event horizon. This conservation law, this integral is only conserved from section to section, only in the extremal case. In the sub-extremal case, you can prove that this is not conserved, or there is no conservation law. And again, the way to prove it is by looking at the characteristic gluing problem for the event on the event horizon. But in any case, I just want to show you conservation laws. By the way, you can see now, right, that if you try to solve the characteristic gluing problem along this event horizon, you can not choose whatever data you want here for the wave equation, whatever data you want here for the wave equation, and glue them and find a solution to the wave equation that matches this data, the given data here and the given data here. Precisely because for any solution to the wave equation, an integral here is equal to the integral here. So if you start with data here and data here which do not have the same integral, that means that this data cannot have come from the same solution to the wave equation due to the existence of this conservation law. And this is a conserved charge for the extremal Kerr. We already talked about Kerr. Kerr has two parameters, mass and angular momentum. Again, a relation of them gives you the extremal case. And in the extremal case, you have one conservation law that looks like that. All right, so what I want to do tomorrow is the following. I want to give you the super general theorem that we have that tells us when we can do characteristic gluing for the wave equation for any null hypersurface on any Norwegian manifold. I'll show you also a few properties. What happens when you refoliate your null hypersurface? Because as you see here, all these conservation laws are on sections, right? What happens if I, instead of considering these sections, I consider this section, but between those two, I consider a different family of sections. like if you refoliate your null hypersurface with sections, and what happens? This is very important because this refoliation here, going from blue to red, okay, it's nice to know for the wave equation, but it's extremely important for the Einstein equations. Because for the Einstein equations, it's the geometry itself that's unknown, not just a C, but it's the full geometry that you're trying to understand. And when you specify the geometry, you basically specify the geometry in a coordinate system, which basically means you specify it relative to a gauge. And that gauge depends on what kind of sections you want to consider. So this refoliation business is extremely important to understand if you want to actually solve the gluing problem for the Einstein equations. So we will do these technical details for the wave equation to understand exactly when we can do gluing for the wave equation and what are the obstructions. And then what I want to show you, this is what I was hoping to do today, but anyway, I want to show you further applications of the existence of these integrals in the dynamics of the wave equation. All right, each of these integrals is very important. Even that one, even the one at infinity, or the one at the horizon, or the inexistence of such things at the horizon. Extremely important for understanding dispersive properties for the wave equation. Okay, so that's what we will talk. And when we finish for the wave equation, then we will move to the Einstein equations. Okay, thank you. Thank you. Perfect question. We will see this in detail, maybe if not tomorrow, the day after tomorrow. But let me show you the questions. These are the questions. Remember, I talked about the phi, which is basically the radius. I talked about the d, which is how you change as you move your derivative along your null hypersurface. That's the question, how your phi changes along your null hypersurface, how your metric, your full metric changes, how your second fundamental form, these are how the shear changes. And for the shear, you see only here we have an elliptic equation, not a transport equation. Here, a transport equation for the torsion. And these are just 4 of the many questions you need to solve. Yeah. At the end of the day, it's a collection of transport and elliptic equations for a system of many components, like 12 components. You start with 12 components on one sphere, 12 components on another sphere. You have equations taking you from one to the other, and you want to know if there is an intermediate object that takes you, basically, that solves this equation, and you have the given boundary terms at both sides. Exactly.
So how much of the derivative along the null surface and then transverse?
Excellent. So for the problem, like for what we will consider, okay. For the Einstein equations, we will have as many transversal derivatives as are needed to make sense of weak solution to the Einstein equation. Okay. For the wave equation, I basically just consider one transversal derivative. I can consider more, but For the wave equation, all I wanted to do is basically fully characterize this conservation laws here. And these conservation laws have only one derivative. See? One derivative. The wave equation is simply it's simply something like if this is L and this is a transversal derivative, let's call it Y. It's L of Y of your scalar field with some equal to something elliptic on the sections. And if this is 0, for example, you see you already have a conservation law for the transpose. Otherwise, you want to know if there is a psi which solves this equation. And these guys are given at both boundaries. That's why with one only derivative is enough. But for the Einstein equations, you need two transversal derivatives to have a system of equations that makes sense. Thank you very much.